In the previous lecture we have discussed the micro to macro level descriptions of carrier transport. So we said the most fundamental level is the individual carrier viewpoint regarding the carrier as a wave. Then the next approximate level is individual carrier viewpoint regarding the carrier as a particle. The next approximate viewpoint happens to be the ensemble viewpoint, where we look at carriers as a group of particles or as ensembles. We analyze the distribution of carriers within a local volume over the momentum. So you take a local volume in a device, look at the carriers in that volume and look at the distribution of these carriers over momentum. Then in terms of the distribution function you try to find out the carrier concentration and current density. And the most approximate or gross level, which is used very often, is that you ignore the distribution of the carriers over momentum in any local volume. Instead you only consider the average value of carrier concentration and average value of momentum in a local volume, and in terms of these quantities you try to model the device. Sometimes we need, in addition to carrier concentration and carrier momentum or carrier velocity, the information about carrier energy as well. So average carrier energy can also be used, and it can be derived from the distribution function of electrons over momentum. We outlined in some detail the method that will be used to derive the current density and carrier concentration from the individual carrier viewpoint regarding the carrier as a particle. So we explained how you can use Newton's laws and get the carrier concentration and the current. In this approach you are deriving the state of each individual particle using Newton's law. The state is defined in terms of the carrier's position and the carrier's momentum. So once you get this information for every carrier, we put this information together and get the carrier concentration and current. Then we began a similar discussion for the development of expressions for carrier concentration and carrier density in terms of the state of the particle of the carrier obtained from Schrodinger's equation. So this is the individual carrier viewpoint with carrier as a wave. We mentioned a few points about the Schrodinger's equation, such as we showed how this equation can be regarded as a balance equation or a conservation equation of probability of carriers, and we showed its correspondence to the continuity equation of the holes. Then we pointed out that while in Newton's laws we use force to specify the action on the electron, in Schrodinger's equation we use the potential energy function to specify the same action. Finally we pointed out that the Schrodinger's equation together with the Pauli's exclusion principle are sufficient to explain most of the solid state phenomena based on quantum mechanical principles. The de Broglie relation and the Planck's relation we said could be derived from the Schrodinger's equation under certain conditions. Now in this lecture let us proceed further and discuss the individual carrier viewpoint based on the Schrodinger's equation in some detail. To begin with, let us understand the Schrodinger's equation for electron in a semiconductor. So what are the forces, or what is the potential that is acting on the electron in a semiconductor crystal? So the potential on an electron in a semiconductor crystal can be divided into these components. Each of these components corresponds to an electric field that we introduced in the context of analysis based on Newton's laws. So UA is the potential because of applied electric field, UB is the built-in potential, UC is the crystal potential, that is the potential because of positively charged nuclei and electrons and holes other than the electron under consideration, and US is the scattering potential. Let us look at the shapes of these potentials. the applied and built-in potentials together have a slow variation with x, something like this. The crystal potential, because of atoms and other electrons, you can include other holes also here, however, shows a much more rapid variation on the length scale of the lattice constant. Okay. So, while the applied and built-in potentials vary slowly, the crystal potential has rapid variations, okay, around the atoms. We have already explained how this kind of a shape results for the crystal potential when we were discussing the effective mass of electrons. Okay. Now, when you put the applied built-in potentials and crystal potential together, the picture looks something like this. Note that all these potentials are being plotted at some instant of time. The scattering potential is a random potential that is not shown here, that adds on to all these potentials. If UA and UB vary slowly on the scale of A, this A is the lattice constant here. UC can be removed from the equation and its effect absorbed by replacing m0 by mn. This is the concept of effective mass. So, that is what is shown here on the slide. We have removed the crystal potential, and as a result the picture has become quite simple. So, you see you only have a slowly varying built-in potential to deal with. So, UC has gone out of the picture and m0 has been replaced by mn. Now, let us understand how this kind of a built-in and applied potential can result. We have explained with an example of the p-n junction when we discussed the development based on Newton's law. Okay. So, there we considered the electric field, while here we can plot the potential for the same situation. So, if you have a p-n junction and this is the space charged region, so under equilibrium conditions, if you sketch the potential, this is the built-in potential and it will appear to increase like this, so something like this. So, as you move in this direction, the potential falls. Now, this is a potential due to a positive charge. If you plot the electronic potential, then it will follow exactly the mirror image of this, a shape like this. So, this is electronic potential. This is conventional potential. Now, you can superimpose a potential because of the applied voltage. For example, if you apply reverse bias, then there is an electric field that superimposed on this, and the space charge region expands and then the potential variation also increases. So, this potential variation here similarly would increase. So, for example, it could increase, say something like this. So, anyway, this tells you how you can get a shape like this for the electronic potential. Okay, that is what is shown here. Now, let us look at solution of this Schrodinger's equation. So, we are following the same approach that we have followed for the individual carrier viewpoint based on the carrier as a particle, and this analysis was based on Newton's law. So, whatever we did for Newton's law, we are doing for Schrodinger's equation. If u is a function of x alone, so here u is a function of x alone, so t goes out of the picture here, then one can show that the wave function psi x comma t can be shown as product of two functions. One is a function of x and the other a function of t, and the function of t is of the simple form e power minus j omega t. where the omega, the angular frequency of the wave, is given by the energy of the electron divided by the h cross. Now the same equation can also be written as E is equal to h nu, because omega is 2 pi into nu, where nu is the frequency. So this is a so called Planck's relation. Now this is what we had said towards the end of the previous lecture, that Planck's relation can be derived from Schrodinger's equation. It is not an independent relation of quantum mechanics once you use Schrodinger's equation as a fundamental equation. Now let us explain this point. Now note that this relation is obtained only for the case when u is a function of x alone. So let us show how, if u is a function of x alone, you get this kind of a form of the solution of Schrodinger's equation. So the Schrodinger's equation is J h cross dou psi by dou t is equal to minus h cross square by 2 into effective mass, because we have removed the crystal potential out of the picture, into, let us write in one dimension, d square psi by dx square plus u, which is a function of x alone, into psi. Now when this is a function of x alone, we can separate psi, which is a function of x comma t in the above equation, into product of two separate functions. One is a function of x and other is a function of t. Now how can you establish this? Well, you assume this result and substitute in this equation and see what happens. So if you assume this result and substitute in this equation, when I am taking a derivative with respect to time, this psi x will not be coming into the picture, and so left hand side will appear as j h cross dou t by dou t into psi x. This is equal to, on right hand side you will have minus h square by 2 mn, and when I am taking derivative with respect to x, this thing will not come into the picture. So you will have d square psi x by dx square, and this we will keep it out for present, plus this psi is product of these two, because this psi of x comma t. So here you will get psi x, and that's t of t has been taken out. Now I can rearrange this equation. I can push psi x to this side and t of t, small t, to this side. So 1 by psi. Now this side is a function of small t alone, and this side is a function of x alone. So both of these have to be equal to a constant, and that constant turns out to be the energy of the electron. Now take the time varying part of the equation, that is this quantity is equal to E. Then you get T by E by h cross. So I am shifting, I am setting this equal to E. So T goes up, and E also comes in the numerator, and h cross comes in the denominator. And then you have j coming in the denominator. So I can put the j on the top and put a negative sign here. Now the solution of this equation can easily be shown to be of the form T is equal to e power minus j into E by h cross into T, of course into some constant coming there. So you see, this is where this thing is the angular frequency omega of the electron wave. So this is where you are getting the relation E by h cross is equal to omega. Okay. Now this is the explanation for this relation here. So it explains how you get the Planck's relation from Schrodinger's equation for the condition u is a function of x alone. Now what about the function psi of x? It turns out that if you assume u of x to be a constant independent of x, then psi of x works out to be this form, constant a into e power plus or minus j times k times x, where k turns out to be equal to the momentum of the electron divided by h cross, or when you transform this relation, because k is 2 pi by lambda, it comes out as p is equal to h by lambda, that is the de Broglie relation. And this p is the classical momentum which depends on the kinetic energy, that is equal to total energy of the electron minus the potential energy. Okay. Now let us establish this part, how you get the de Broglie relation and how you get psi x to be of the form a e power plus or minus j k x. For this purpose we look at the same equation, but now we work with this side. Okay. So this part of the equation, if you work with this part of the equation, then it reduces to this quantity is equal to E times psi, and transforming that your equation becomes minus h cross square by 2 mn into d square psi by dx square plus I am sorry, here a u was missing that I am introducing now, and that u we are going to write it as u naught, because we are going to assume u is a constant with x. Here u was a function of x, but here we are going to make it a constant u naught minus e into psi. So this is equal to 0, right? But let us transform this as E minus u naught, because E is the total energy and u naught is the potential, so that this remaining part will show the kinetic energy. So we write it as E minus u naught, and there is a negative sign here, so there is a negative sign here also, so both negative signs go away and again you have positive sign, and this is 0. So this is your equation, which you can further transform. I can shift h square by 2 mn, h cross square by 2 mn to this term. So d square psi by dx square plus 2 mn into this quantity by h cross square into psi. Now I can call this quantity as k square, then my equation will be of the form d square psi by dx square plus k square psi equal to 0. Now this is a very simple differential equation. You know that its solution will consist of two components, psi equal to e power jkx with either a positive sign or a negative sign. Both solutions are possible, you know, it will satisfy this equation. Now let us put a constant a here. Now what is this k? this k is the square root of this quantity. So k is equal to square root 2 times mn into E minus u naught upon h cross. But this quantity here is nothing but the kinetic energy, the classical kinetic energy. Therefore, square root of 2 mn into kinetic energy, as you know, is equal to the classical momentum. So therefore, you can also write this as the classical momentum P by h cross. So classical momentum, and from here you get this relation that is shown on the slide. So k is equal to p by h cross, or p is equal to h by lambda. Okay, so this is how we have shown how the de Broglie's relation arises. Okay, and we have shown that for many situations we can use a solution of the Schrodinger equation which has this form, that is the psi of x comma t separated into psi x into t of t, where this is of the form e power minus j omega t, and for the particular case, so this form works when your u is a function of x alone, and psi of x can be shown to be of the form a constant into e power plus or minus j times kx if this u is independent of x and is a constant. So these aspects will be useful for us when we discuss solutions of the Schrodinger equation. Now let us take a particular situation, an electron encountering no collisions in a uniform semiconductor under equilibrium, that is a free electron with an effective mass mn. So what is the solution? So you will recall that we had discussed exactly the same situation when we applied the Newton's second law and tried to derive the state of the particle. So here we want to do it using the Schrodinger's equation. See what is the difference. So u of x, let us assume it to be 0, because there is no applied electric field, there is equilibrium condition, so no applied electric field, no built-in electric field as well, because it is a uniform semiconductor. And let us assume that electron has a kinetic energy E naught or a corresponding momentum P naught, which is equal to square root of 2 times mn E naught. The solution of this, just now we discussed that this form of the solution. So it has been plotted as a graph. So it is like a sine wave where the wavelength lambda is equal to h by p naught. Now what do you derive from this information? We derive the fact that electron location is completely uncertain, that is the delta x uncertainty in the location of the electron goes to infinity. Now how do you derive it from this condition, from this solution of the Schrodinger's equation for a free particle? So here you have to invoke the physical interpretation of the wave function. So you will recall that the wave function psi by itself does not have a physical interpretation, however its modulus square, that is the psi multiplied by its complex conjugate, this has the physical meaning of probability density or probability distribution. So if you take a one dimensional situation, then if I plot the modulus of psi square as a function of x, let us say for the kind of problem that we are considering. So psi as a function of x is a sine wave, so psi square would look something like this. Like that, and this will go on to x equal to infinity, and on this side to extending to minus infinity. Now if I want to know what is the probability of finding an electron, let us say within some interval like this at this location, then the area under this curve, that is the integral of psi square over the interval in which you want to find the electron. So this area indicates the probability that electron will occupy that location. Now since this goes from minus infinity to plus infinity, it means that the electron can in principle be anywhere from minus infinity to plus infinity, though it is true that there are more likelihood that it will be here or here or here near the peak locations where the probability density is maximum, but in principle it can exist anywhere. So now this is the interesting result that the Schrodinger's equation has given us. According to this equation, if you have a free electron which is not acted upon by any forces, and you think that it has a specific energy or momentum, then you cannot locate this electron anywhere. Its location is completely uncertain. So this is what is hinting towards the problem that if you regard the electron as a wave, you cannot get its momentum and its location precisely. If you try to give its momentum precisely, then you do not know its location. Okay? Now we are not comfortable with this kind of a thing, because from our particle experience we would like to locate the electron at some point. Now let us see what happens if you try to locate the electron. So let us say the potential energy is 0, it is a free electron, and the electron location is x average with uncertainty delta x. So we will not try to locate the electron precisely first. Let us say we allow some uncertainty. Why? Because right now we are faced with a problem where the electron is not possible to locate at all anywhere, it can be anywhere. So let us go step by step. Let us say, okay, we will accept some uncertainty, not so much of uncertainty from minus infinity to plus infinity, but some uncertainty. Let us say we want to locate the electron at some x within an uncertainty delta x. That location where we want to locate it is called average location, x average. Now what is the wave picture for this case? So in terms of the wave picture, the psi x as a function of x would look something like this, because we interpret the wave function psi as a function whose amplitude square gives you the probability of locating the electron, and since psi has to be alternating and therefore psi square also is changing, the only way you can locate an electron within some uncertainty, finite uncertainty, is to have the wave function limited in some way to that region. Therefore the shape of the wave function looks something like this. So you can see that the wave function is dying out, its maximum at x average, and it is dying out. Now this is the kind of solution you are looking for. Now how can you get a solution of this sort starting from a wave which has a particular wavelength, right? So we know that we have a wave like this. So if your psi of x is like this, a regular wave, then we know that this wave corresponds to a particle which has a precise momentum, which is given by, if this is lambda, the momentum p is equal to h by lambda. starting with this wave, how do you get a wave which is maximum at some point and decays thereafter? Okay. Case when the particle has to be located in some uncertainty would be something like this. It will be maximum here and then it will go on decreasing. Same thing on the other side. And this is the so called location x average. And this roughly tells you the uncertainty delta x. So to get this kind of a wave packet, this is called a wave packet because we will see that this can be composed from individual waves of continuously varying wavelengths. So something like this. So you start with a wave which has an average wavelength, lambda average, which corresponds to the energy of the particle, average energy of the particle. How? So if you have lambda average, it will give you average momentum equal to h by lambda average, and therefore you can associate a kinetic energy, average kinetic energy, as P average square by 2 times the mass. Okay? So that is how you can choose the average wavelength for the given momentum or energy. And now you superimpose on this wave waves of wavelength less than lambda average and more than lambda average. So you do a superimposition as follows. For all the waves, let us locate their peaks at the location x average, which is where we want to locate the particle. And then on either side, the if you add the waves, you can easily see that as you move away from this point, the amplitude of the sum of these waves will go on decreasing. For example, look at the location here. You have a positive value, then you have a negative value here, and you have another negative value here, a small negative value and more. So if you add these two, the negative values will reduce the sum from the positive value, right? And you go farther and farther away, you will find that for a large number of waves, the amplitudes will randomly vary, and therefore they will all sum up to very, very small values. So that is how a packet of waves like this with continuously varying lambda around the average value. So the lambda decreases from the average value as well as increases from the average value. You add a large number of such waves, the more and more waves you add, the more rapidly this function will decay, right? So supposing you want a function here which is very sharp, you want to locate the electron very precisely, and you want this kind of a function for psi square, then you have to add a very, very large number of waves. So now what is the result you get? Since each wave like this has its corresponding momentum, the various waves that you are adding have their own momenta, and therefore you are not getting a precise momentum. You add up the momenta of all the waves, so your momentum now is having uncertainty. And as we have said, the more precisely you want to locate the particle, the larger the number of waves you have to add, therefore the larger is the uncertainty in momentum. Okay? Because all these are waves of different wavelengths, therefore they are waves of different momentum. Now that is the important conclusion you get. So localization increases as more waves are superposed, widening the uncertainty delta lambda and so delta p, and taking the limit for precise location x average, delta x should tend to 0, and this is only possible if delta lambda tends to infinity, because you have to add infinite number of waves, resulting in delta p tending to infinity, that is a particle whose momentum is completely uncertain. So you are getting the other result, that if you try to locate the particle very precisely, its momentum is uncertain. Earlier we showed if you have a particle with a precise momentum, then its location is uncertain. That is this case. Now that is the problem. Okay, if you take the wave approach, we are not able to simultaneously specify the position and momentum of the particle, and therefore a simple formula that we used based on classical mechanics, which help you to derive the carrier concentration and momentum from the locations and the momentas of the various particles, that cannot be used. Now, since this is an important point that you cannot specify the momentum and position of a particle precisely when you regard the electron as a wave, this is a very fundamental result. So let us make ourselves comfortable with this result with the help of an analogy. Let us take a practical case and ask the question, where is the wave and what is its wavelength? Suppose you consider a wave like this, which has a well defined wavelength, right? So if you look at the wave, you can definitely identify its wavelength. However, if somebody were to ask you the question, where is the wave, what is its location? Now you know that you really cannot locate the wave precisely, it seems to be going everywhere, right? It exists everywhere. So this is an example where if you know the wavelength precisely, you can't tell the location. Let us take the other extreme. Now this is a wave whose location you can specify with fair amount of certainty, right? Somebody asks you the question, where is the wave? You can say, yes, it is here. You will associate the location with the peak. Now if somebody were to ask you, but what is its wavelength? Well, you find no wavelength of this wave, so it has an ill defined wavelength. So you see, if you try to locate, if you know of a wave which can be located precisely, you really can't associate a wavelength with it, you can't identify any wavelength. Okay, so the model is, for a wave, the position and wavelength both cannot be defined precisely at the same time. Now let us transfer this conclusion to our practical case of our practical problem of getting the carrier concentration and the current density of an electron from the wave viewpoint. So if regarded as a wave, electron's position x and momentum p cannot be defined precisely at the same time. Therefore, the classical formulae for nx, t and jnx, t based on xi and pi have to be abandoned. Xi is the position of the ith electron at any instant of time, and pi is the momentum of the electron at the same electron at the same instant of time. Now if regarded as a wave, electron state is defined by psi I x, t, one function, right, which has both time and distance variable. In place of two quantities, the location as a function of time and momentum as a function of time. And therefore the formulae for nx, t and jnx, t should be based on the psi I x, t, that is the wave functions of the individual electrons. Further, if regarded as a wave, the electron pervades throughout the device. On the other hand, its presence is localized to a point when regarded as a particle. So you see, this is a very interesting information that we get. If regarded as a wave, right, it pervades all over. Even in the case you can see here, when you are trying to improve the location of the electron, you have the wave existing all over. Its amplitude is less, no doubt. So the probability of finding the electron elsewhere is small, but it is not zero. That is the point. So it exists everywhere. Therefore, the wave functions of all the n electrons, psi i's of all the n electrons, determine the number delta n of electrons in a local volume delta v at x and the current due to these delta n electrons. So you will recall when we did the current and carrier concentration modeling based on Newton's laws, we divided the device into local volumes, right. So we did something like this. So we said this is the device in which you have n electrons, and then we took a local volume delta V, and then we counted how many electrons here out of this n. So this statement is regarding this situation. So the wave functions of all the n electrons will determine delta n. Okay. So now from the wave approach, if you want to find out what is delta n here, the wave function of each of these electrons will also have to be taken into account, because from the wave point of view each of these electrons pervades all over, though its probability may be very high at some locations, but it is not 0 at other locations. So even if I want to know how many electrons are there here, I should consider the wave functions of these other electrons. Therefore we can set out the procedure as follows. At any t, the psi I x comma t's of all the n electrons within the device determined from the Schrodinger's equation yields a number delta n of electrons in the local volume delta V located at x, leading to this formula: nx comma t is equal to psi I x comma t square for all the n electrons summed together. Right. Now this can be, this formula can be derived very simply as follows. So concentrate on this volume delta V. Now take the wave function of each of these electrons, that is psi I, square it, integrate it over this delta V. That gives you the probability of finding the ith electron in this volume, right. Psi I is the wave function of the ith electron. So when I integrate over this, then I get the probability of finding this electron in this volume. Like that I should do for all the electrons, all the n electrons. So that is how you get here. Then what will you get? Then you will get this number delta n. So the number of electrons here is delta n. So you will get delta n here. So if I now push this delta V here, this ratio delta n by delta V is nothing but your n, carrier concentration within this local volume wherever you are located it. Let us say you are located at some x here, right. So that is the result. Let us look at the result for the current. So from a knowledge of psi I x t's of all the n electrons, we derive the current expression as follows. Now let us explain this current expression, right. How do you get? We can link it to the expression based on the classical approach, right, based on Newton's law approach. In the classical approach, if you recall, your current expression was as follows: Jn was because of this delta n electrons, right. So you found out the momentas of each of these electrons within the local volume, that is Pi. You divide it by the effective mass and sum up for all the delta n electrons, then multiply it by minus q. That gives you the current density. Now supposing you extend this approach to the wave point of view. Now you know that from the wave point of view, the momentum Pi can be expressed as h cross times Ki, where Ki is the wave vector, okay, for the ith electron obtained from the wave function. So look at this wave function here. This is the k square and this is the k, right. So for the ith electron you must find out what is this k. what is the energy, depends on the energy. So h of ki. Now however, as we said, the wave pervades everywhere, so I must use all the n electrons. Now the probability that ith electron will be in the local volume delta V is probability psi I square, and so I should do this for all the n electrons. So you see what is happening is, when I move from the classical picture to the quantum picture, the delta n is getting replaced by all the n electrons, but what is coming here is the probability density, okay, of finding the ith electron in that location. Now it turns out that this simple approach that we have adopted corresponds to the case of a plane wave, that is a wave like this, okay. But you know that in practice, supposing you are talking about locating a particle, then you will have a probability distribution function like this, okay. In other words, you can have a wave packet, so you can have different types of wave functions. So you need a more general result that is applicable to other cases as well. It turns out that more generally this quantity works out to, we are not going to do a detailed derivation here, but we will only explain the result. This quantity works out to the conjugate of the psi I multiplied by the gradient of psi I minus psi I into gradient of the conjugate of psi I by 2 times j. So this j is coming because when you do this exercise you will have the numerator complex, so you are dividing it by j to make it real, and then there are 2 terms here, they contribute, both of them contribute, and therefore you divide it by 2 to get this kind of a relation. Now how do you explain this kind of a expression here? Now you know that we have said earlier that the current is the probability current. So electrons are moving from one point to other point because the probability of finding an electron at one point is higher than the probability of finding an electron at other point. Therefore the current depends on the gradient of the probability. That is what is coming here actually. That is why you have gradient terms here. So because of this there is a momentum generated, because there is a probability gradient, there is the driving force for motion and a momentum is generated. So that is how this is coming into picture here. So this can explain the form of the equation that you see here for the current density. Now we have come to the end of the lecture. Therefore let us make a summary of the important points. Now this entire lecture was devoted to finding out the carrier concentration and current density, okay, from the state of the individual electrons as determined from Schrodinger's equation. So we essentially discussed the individual carrier viewpoint regarding the electron as a wave. So first we explained how the Schrodinger equation looks like for a semiconductor crystal, what are the various potentials that the electron is subjected to. Then we discussed solution of this Schrodinger's equation for a very simple case, and we showed that because of the difficulty of specifying the location and momentum of an electron simultaneously and precisely, the formula for carrier concentration and current density becomes more sophisticated, a little bit more complex than the case of classical mechanics.
Sir, I have a question. Can you clarify once again how J comes on the left hand side of the Schrodinger equation and -1 comes as the coefficient of del square term?
Okay, so your doubt is related to this equation here, how j arises here and why -1 term comes here. When you see the correspondence of this equation to this equation, here you do not have any j or anything like that, and here the coefficient is positive. So let me clarify that we are not discussing here the derivation of this equation, but we are trying to explain how we can make ourselves comfortable with the form of this equation so that we remember it for long time. Now the way to understand it is very simple. Since psi is the solution of a wave equation, psi is a travelling wave. Now you know that a travelling wave always of the form always has a coefficient like this, so into something, so psi is equal to something into this. So here you see kx minus omega t. Now one may discuss about the sign here, should it be minus or plus, and should this sign be here plus or minus. We will not get into that discussion right now. Let us just use this form which we are very comfortable with, which we have used in our earlier courses, and explain how this sign arises here and how this j arises. Now once you assume a form like this, clearly when I differentiate psi with respect to t, I will get a minus j out. Okay, there is a negative sign here and there is j, so I will get minus j out. But ultimately the coefficient of the term here, when you differentiate, you will get psi itself multiplied by a minus j term. So the coefficient of psi, you can see here, this quantity is real, right. So everywhere after you perform the operation indicated here, look at the whole term, it should come out as some coefficient into psi. That coefficient should correspond to the coefficient shown here. For example, the coefficient here should be positive. You can see that coefficient of the del square term here is positive, and similarly the coefficient of the term psi term here should also be positive as shown here. So now you can easily see that by differentiating with respect to time, if I am going to get a minus j out, to make the coefficient plus 1, I have to multiply minus j by j, then minus j square would become plus 1. Similarly, if I differentiate with respect to x twice, which is what this asks you to do, so take this and differentiate twice, I will get once j with one differentiation, second differentiation will give me again another j, so I will get j square out, and j square is negative, whereas I want the coefficient to be positive as shown here if it is in a del square form. Therefore I multiply the term by minus 1, so that this minus 1 multiplied by the minus 1 coming out of this operation makes it plus 1.
Sir, can you similarly clarify the sign of the third term, u psi term?
Yeah, your probably your doubt is that here you see a negative sign as coefficient of the p term, which is the p term here. Similarly, your doubt is why should the coefficient of this term here be positive, right, whereas here it appears to be negative. Well, as we have discussed earlier, that this term is a source or a sink term. For example, p minus p naught here could be positive or negative. Thus after the negative sign is attached to this, this whole term could be positive or negative. It turns out that here this term is written as a positive term. Okay, it is plus u into psi, and it is a source term actually. It gives rise to probability. It is not a sink term, it is a source term.